Okay, so you see the shared screen, correct?
Yeah.
Good. So far in this class, we talk about several general meta theorems that can be applied for general networks. We can make it them trees. We talk about some important problem like bias network design and others. We talk about special graphs and the approaches or the hammers that exist for them. For example, for important class of sparse graph, which is like H-minor free graphs or bounded diversity graphs. And there are others, of course, these are like some kind of the tip of the iceberg. You can always read through some algorithm for expander graphs, etc., that are also interesting. Here, I wanted to mention a little bit about just the big data and big networks. That's another thing that is actually interesting. And these are the networks that they need their own thing. Again, this is just the introduction. You may have some separate class on that one, but I just want to give some interesting things there. Some of them that are actually quite interesting. Some ideas here. In particular about streaming, we talk a little bit about the MapReduce as well, but this is the thing. Good. So let me. So if you're talking about lots of real world networks, which are like the social networks, like this Google Plus maybe does not exist. Twitter is X now. Facebook, there is now other things like threads essentially. They are changing, they are coming and going, but these are big networks, biological networks. These are brain networks, especially brain connector network, computer networks, especially like internet IP networks, web graphs, transportation network, and these are become bigger and bigger. And we need to handle them. And this is important. So we will try to talk about the models that we can handle these huge networks today. Here, before going there, I want to also give a summary of when we talk about different algorithms in this class. I just wanted to just mention an overview of them essentially. This is actually a nice way of seeing the algorithm that we are talking for network design in general. In this class, we talk more about approximation algorithm, or we talk about fixed parameter algorithms and classic algorithms as well. So this is a very nice view of, essentially this. The credit goes actually to Eric Demain. He presented this way. So generally, in algorithmic goals, we have three goals that we try to satisfy. We want to get the correct solution. Correct means optimal solution. Good. We want to get fast. Fast essentially means polynomial time. Fun time means essentially linear or or super linear, like quadratic or something like this, or cubic even. And we want to solve hard problems. Generally, hard problems means these are NP-hard problems. And lots of natural problems are NP-hard problems. As I mentioned, probably the most interesting problem that we can solve within P are matching problems. And the other one is matroid intersection. These are like this matching means weighted matching in general graphs. And the other one is the matroid intersection. What's that? No, not in general graphs. In bipartite graph, actually, you can do it in terms of matroid intersection, but this is not general. In general, it is that. These two are probably the hardest P problems. And again, I think the credit goes, these two Jacket Mons, always I give the credit. He defined somehow the probability, essentially the whole, this matching algorithm, even by current standard, today is one of the most complicated things that we have. And he developed a time that there was not much polynomial time algorithm. I think he really deserves a Turing Award for this. Okay, so this is the things we talk about it. Lots of our problems actually are NP-hard problems. We talk about lots of them: Steiner tree, Steiner set cover, Steiner forest. I mean, you name. The issue is that assuming P not equal to MP, we cannot solve all of them at the same time. So we need to pick two of them. All goals are not possible. We cannot get the optimum solution in polynomial time for NP-hard problem, at least so far. So we need to choose essentially only two of them. So if you forget about hard problems, then essentially we have the correct problem, fast polynomial time, as I mentioned. This means essentially most early algorithms, and in particular, metro intersection, as well as maximum weight matching or weighted matching, essentially in general graphs. And lots of them undergraduate algorithm, except these two problems. These are like quite grad courses, grad classes, essentially you need to teach this class, this problem. So that's essentially the problem in P. The other one is essentially approximation algorithm that we talk a lot in this class. There we are essentially forgetting about correctness. We don't get the optimum solution. Then we want to get fast means polynomial time algorithm and for lots of NP-hard problems. And of course, when you don't want to totally forget about correctness, we say that, okay, we cannot get optimum solution. We relax it to near optimal. And we talk about like constant factor approximation, log n approximation, or something you can even talk about square root of an approximation, for example, for label cover. And in particular, PTASs means polynomial time approximation scheme, which essentially means within 1 plus epsilon factor for any specified epsilon. Epsilon generally is constant, but can be actually 1 over log n or something like this. So that's a view that you can see actually what are the approximations. So this is like the different type of algorithm that we talk essentially for network design. Then go next one. The next thing that we are talking about are like, as we talk about it, are fixed parameter algorithms. In the fixed parameter algorithm, we talk about them when we talk about bidimensionality in particular, because the applications were both approximation and fixed parameter algorithm. Here we want to get the correct solution, means optimum solution. We want to solve NP-hard problem, but still, okay, fast. Maybe we forget about fast. Of course, we cannot totally forget about fast. Time is very important. There we will relax it, and we will say, okay, you want to get, you want to confine the exponential growth to some okay, good. So here we try to confine the exponential growth to some parameter k, which is often the optimum solution in fixed parameter algorithms. This is something different from the input size n, and the idea is that you want, I mean, like a naive way is that if the optimum solution is k, so for example, for vertex cover, you can get set of all sets of size k in the vertex cover and talk about them. But the running time generally can be exponential. It can be n to the k, which is not good. We generally want to get it something like f of k n to the order 1, like 2 to the k to the n, or 2 to the 2 to the k to the n to the 3. And this the whole idea that n might be very large, but the solution might be small, or the parameter, still we can get it essentially solve the problem. This is again some kind of formalizing backtracking algorithm or branch and bound algorithms that you want to get some guaranteed on the running time of this. That would be the essentially fixed parameter algorithm. And in particular, we talk about this 2 to the square root of k times n to the order 1. This came out of bidimensionality that we talk about it. And these are sub-exponential time algorithm. And for example, for planar graph, you can do that thanks to bidimensionality. And these are tight. You can say under ETH or other assumption, you cannot do anything better than that. These are the things that we talk about. So some kind of reviewing the things that we have done. Then what else? Another thing which is interesting, it is algorithmic game theory. So probably, I mean, this is part of network design, essentially. Whenever you have the network, you have lots of players in this network that they are, maybe the nodes, maybe these are some of the players that they can move on the nodes, pebbles, etc. There are lots of things that you can consider game theory on top of the networks. And these are the things that probably we will talk less in this class, but there is another course that I will present about algorithmic game theory that actually, that's the graduate course. Later we will talk more about those stuff. You can see it more. And the whole idea is that you are considering some of these goals. Again, we cannot have all of these goals at the same time, but some of them we can choose with a new goal as well. The thing is that generally in the algorithm design, the goal is that we try to just design some algorithm for some dumb objects. That we say that, yes, if you are in a line, you want to sort them, you will just essentially swap to essentially two items, and they will be swapped. However, in the algorithmic game theory, we are talking about selfish agents, and each of these agents, they have their own incentives. These nodes of the network, for example, this is something that we will talk about network creation games, that each node in the network has his or her own incentive to which node it should connect. And this is the real thing that happens essentially, for example, for lots of local like network providers, etc. For any other cases, essentially, you may think about these people that are going essentially through the roads from one place to another place, and then they have their own incentive. Here, the idea that these agents, they have their own incentives. And again, a simple example is a line. If the people are in a line to get essentially food, you cannot easily come and say that, oh, I want to swap these two people. The people will be upset. So why do you want to swap? Oh, I have some greater good here for that. I want to do that. But of course, the people will not agree with that things, or will be very upset with you at least. So that's algorithmic game theory is a very important thing in network design. And again, it needs the whole different class essentially. We may touch very, slightly in this course. Now, another thing which is very important that we are talking about them are streaming or online algorithms. That's also another thing. Again, we have some of these goals. Here, the idea is that we have some kind of partial access to the input. So that's essentially the similarity of these algorithms. So it is a streaming online algorithm, as well as maybe also I want to add another one about dynamic algorithms. So dynamic algorithm are the same. So here, generally this happens, either to the big data nature of the input, or some of the things that, we may not have the data essentially at the beginning. Here we don't have essentially access to the whole data, and the data comes bit by bit. That's essentially the idea of streaming online algorithm and dynamic algorithms. We will talk more about this one. There is another one essentially like this kind of in the big data algorithms. This is also this concept of essentially MPC, massively parallel computation. I will briefly talk about it, but less here. And I will give some references to that. So that's another one that we have access to the data, but the whole data is so big that we need some essentially particular algorithm for doing that. So that's somehow so far is a summary of the algorithm that we consider for network design. And these are like, in general, the summary of algorithm design in some sense. If I want to present it, like if you want to present your work, if you work in the algorithm, you want to present it, what are you doing that? This is actually very good thing. Again, some part of it is the credit goes to Eric Demain and the rest to me. They could essentially make it such that we can present all essentially in a few slides. What do we do essentially in algorithm design? It's a good thing that you have it in your mind if you want to present it in other places, etc. Now, here we mentioned lots of real networks. So we talk about real networks. Always, I mean, these algorithms that we design, we really want to apply them on some real world network design. As I mentioned, for example, for buy-at-buck network design, I mean, these are some of the things that we have implemented at AT&T, or like some of our other bigger networks that for affinity clustering, these are some of the algorithms that currently are in use. We designed this algorithm, but they are currently in use at Google, several places. So we want to essentially apply our algorithm to real world, at least some heuristic based on that. Some of this, lots of them are big. All these that I mentioned, like about social network. Google Plus, again, this is not the Google Plus anymore. That is dead almost. The Twitter is X, and Threads and others. These are like very large networks, 10 to the 9 nodes. Biological network, brain connectome things. These are essentially some of the things that they will consider the brain. And then from the brain, they can create a network. So there is some standard way, essentially, from the elements of the brain, they can create actually this one and they can represent. Computer networks, internet IP or web graph, just 2 to the 33 two nodes, essentially. If you have 33 nodes, bits essentially to represent it, potentially we can have such kind of large graph. Transportation, also it becomes very big, lots of details. Like if you consider, for example, like US road maps, for example, by Google Maps, they have 10 to the 8 intersection nodes. Each of them would be a node essentially in the graph. Lots of these graphs, I mean, these are more, I will say these are sparse graphs. And again, we talk about some ways that you can do the sparse graph, but even a sparse graph, when they become so big, handling them is non-trivial. Good. So we have lots of natural problems on this big graph that you want to solve. You want to find essentially botnets or spam detection, essentially. You may want to do community detection. Community detection in particular is the this problem is in particular dense subgraph. So dense subgraph is a particular problem which is actually very interesting and important on this problem. Reachability distance between the nodes. I mean, that is lots of this kind of reachability or distance you can define between nodes. And this is very important because that's the way that all the packets essentially routed through the network. You may want to do summarization, sparsification, clustering, visualizations. All of them, these are super important. These are the things that we need to do it on this big graph. And in all of them, when you try to solve this problem, these are like some of the basic problems that they will come. As I mentioned, you will go there at the end of the day, you see that the techniques that you are doing there, or some of the procedures are some of these famous problems like matching or vertex cover. These are very similar in the same thing. Set cover or hitting set. Dense subgraph, as I mentioned, cut problems, connectivity problem. These are some of the things that we already discussed. And these are like the, as I mentioned, cut problem, connectivity problem, some kind of assignment problems, like matching or essentially set cover. And the denser subgraph is another thing essentially is more like the something in between. These are some of the general problems that we are considering and we want to solve. Great. So it is like all motivations are important. I can say essentially that like when you want to talk about streaming, you may want to actually think what is the good story that you can put it, some real world story. And this is some of them that we have spent actually time uh, with Eric Demain essentially to actually think about the motivations and try to find the best motivation. And the motivation had a big, essentially, like just maybe changing the motivation, like a grant maybe got rejected before, but the nicer motivation actually got getting. So this is an interesting thing. So for this kind of, we generally for the streaming algorithm, this is the nice essentially motivation that we have some kind of partial access to manipulate the data. It might be the case that this is stored in relatively a slow, huge external hard drive, blue disk drive. This is actually something that I need to deal with it. So if you have a big data, you want to handle it somehow, like outside thing. Reading it would be large, and you know that this big data is there, like big network is there. It might be in the cloud. I mean, this is like you have put everything on the cloud and then just reading it, you don't have even a space to bring it, to download it. It's so huge that you cannot. It might be the case that it comes too fast and is too much to store. Again, all of them are very practical things. This is like, for example, internal routers. It was some project at AT&T like some time ago, and I'm sure that similar companies like Verizon, AT&T, others, they have it. They have this router that this routers essentially send the packets through the network. They really want to get some estimate how much is the traffic, etc. There was actually a very nice project. There were several papers there. They were just, and the issue about these routers is that these are essentially, I would say computers, but very limited computers. So this is, so these are like computers that you can run some code, but this was actually some, again, real world thing that like the number of lines that you can write in the code of this router is very limited. And they have a limited memory. You don't have to, I mean, you cannot essentially just put them, you will just store it on something, like store on some other things. And it is super important. This was, again, some practical thing that I think AT&T, that was like, again, several years ago, they just changed the router algorithm and just a little bit delay. This is the whole essentially congestion and network breakdown. Because if these packets, there are billions of packets are going essentially. As I mentioned, each email, everything is divided into a small things. All things that you will download will be into these packets. These are a small thing that they are going through different paths, and as little as a little bit extra, the algorithm takes a little bit more time. This is the whole congestion that happens, which are super important. These are like realistic assumptions. And this is the case that so you have this partial access to that, and you may not have essentially access to supercomputers or clusters to manipulate it. If you have access to supercomputers or clusters to do that, that would be essentially the map reduce approach, or essentially MPC, I will say. So MPC is the massively parallel computation. This MPC, or massively parallel computation, in particular MPC Spark, these are like some of the things that the people are using it, especially Hadoop, etc. These are the things that you have access to supercomputers. You can put this one. It means that you have essentially access to computer, either to cloud computing or supercomputer. Essentially, supercomputers means clusters. It essentially means cloud. If you have access to that, then you can maybe handle it. But lots of computers, lots of resources, lots of money. If you don't have it, lots of people may not have it, and this is expensive, essentially. So there are some examples, as I mentioned. So, like, for example, an internet provider may need a statistical data of packets through the router. They want to see from this route, these packets through the network. You say from which destination to essentially from which source to which destination. You want to get some statistical data. That was a real thing that was happened essentially at, as I mentioned, at AT&T when I was there essentially. And sometime before my time, essentially. These are super important, and you need to guess this one. You don't have the resources, and these are essentially the information comes on the fly. Another example, you may think about you have your cell phone and you want to verify a blockchain. It is 33 gigabyte of the database. I think that is like, I think back in 2016 or something. Probably it is now, it is around 80 or even more than that. So it's a large things, and you want to do this, verify some kind of blockchain. So, and you don't want to download it. You have a limited thing. You don't want to use essentially your data for that. Another example is essentially some rare events that may need ad hoc search over heterogeneous data from multiple sources, not indexed for this. So there was several years ago that was this Boston Marathon bombing. Essentially, it was some terrorist activity. And there, essentially, there was two brothers that they were doing that. And they actually killed several people. It was like a very horrible thing. That took actually, I think one of the people was killed. I think was that was happened in Boston. I think one MIT police officer actually was killed during this thing. Essentially, finding this, it took a few days to find who were the people who have done that. And this, you have the data, for example, to the cameras, others, essentially different data. That's the meaning of heterogeneous, means that they are coming from different resources, they have a different format, and you want to find the things. You don't have the access. So this type of thing that you have a partial access as actually makes sense, and you want to find possibly some algorithm that you can make these things as fast as possible. Again, this is some idea that, I mean, like why like streaming algorithms are useful. These are not just useful because somebody considered it, but actually we are considering lots of basic algorithms that can be used for. Another example, for example, the transactions, like for the banks. So there are tons of transactions, essentially. This is some generalization of blockchain. So for the banks or the financial system, tons of transactions that are happening. And you don't have time to include all of them. And actually, because of the privacy also, you may not be able to preserve them all. So you want to just handle them on the fly and they are gone. That's the thing that we are talking about today, more about streaming. Yeah. So that's the thing that we consider essentially this kind of streaming algorithms. That here it's a very simple, but it's very fundamental thing. We are assuming that the data arrives in a natural order, which is outside of algorithms control. Sometimes we consider worst case, sometimes we consider the random order case. We are assuming that there is enough data or enough memory actually to store a small summary of this data. And we assume that this or algorithm can view this stream once or only maybe a few number of passes. This few number of passes happen, for example, if you have this kind of outside like external hard drive or blue disk that you can go through it a few times. This model is, I mean, in particular, very useful for some kind of thing that is temporarily dynamic data, like online social network, Bitcoin, or essentially financial transaction or internet routers. All of them are the ones that actually are very good for this thing, that they are coming in some random order. You have some limited thing, you need to compute something. And as I mentioned, as a byproduct of this is that like you can handle a very complex network on like your laptop. And I have done it essentially for some of these project grants that I had it. I had some external drive and I have done it with my own computer. I will mention it at the end of this. Good. Now, as I mentioned, there are other things like MapReduce, MPC models essentially to handle this algorithm. So MPC in particular to handle the big data. So both MPC. So I mentioned some graph algorithm like matching or a string essentially edit distance that you can use MPC on big data. This is already presented in my introduction to algorithms course. The last session I'm talking about these things and I'm talking about the application for this problem. I talk more about also streaming algorithms in the algorithmic lower bound course. Again, these are like the videos are available online. You can take a look at it. So I will talk less about this. I want to talk about more positive algorithm that exists essentially for streaming algorithm. And in general, this is important. So when you work on the networks, there's always some similarity between these. These three algorithms are very important. MPC, streaming, and dynamic algorithms. All of them in some sense are doing the big data and the partial access in some sense. And interestingly, there are maybe some cases there are some black box essentially approach that you can get one from the other. There is generally not a black box, but if there is some MPC algorithm, that means that maybe you should think about if there is some streaming algorithm. A streaming algorithm in particular are very simple algorithm. You cannot do that. Generally, the algorithm can be generalized for MPC and dynamic algorithm. The same as well. Like if there is some MPC, probably there are some kinds of streaming algorithm, some interesting things. Maybe less this direction because again, streaming and streaming algorithms are a bit simpler. MPC it might be more complicated, but sometimes also if there is an MPC, there is a streaming algorithm and dynamic algorithm. So this is the approach that you should consider. All of these three things are very important, especially for current things. Dynamic algorithms are super important. Also, the ideas I mentioned. So you may want to, for example, consider this kind of advertisement, internet advertisement. You have 20 milliseconds to show some ads. It means that lots of these computations that you need to do, which ad you should show or and which from which advertisers, etc. Lots of them should be done on the back end in a more dynamic fashion. It means that everything should be cached. It should be pre-computed. And that's the whole idea of dynamic algorithm, essentially. You need to update everything that comes, such that it does not take any particular showing ad should not take that much time. That's essentially about dynamic algorithm. Anyhow, these three set of problems are very related. And generally, if one exists for one, there are others that exist similar ideas or some nice extension of these ideas for other things. And you should always take a look at it. As I mentioned, for MapReduce in particular, for MPC, MapReduce or Spark. Spark is the typical thing that the people are, there are some companies even based on that, like Databricks essentially is based on Apache Spark. These are interesting things that you should know both in practice and in theory nowadays. Good. But we will talk less about them and we'll talk more about the streaming algorithms for networks here. Again, you can get the videos online. Good. So here in this streaming network model, you have, this is the simplest one that we are considering, that you get one chance to see the edges. So each edge you are seeing it once. The space must be sublinear in the size of the input. That's the preferable thing. And you need to, you also want to minimize the analyzed time to process each edge or accuracy of the answer. So the space is an important thing limitation because you have a space limitation, you don't have it. At the same time, then you may also talk about the running time for each update. That might be important, but even just the space itself is quite actually interesting. And lots of theories there. There are some variations that you, instead of one pass, you may have a small number of passes. Here we will talk more about one pass. And another one, which is very interesting, it is insertion only version that you just insert the data, or you may have edges added or deleted, which is a dynamic version. And this is called dynamic streaming. And there are dynamic algorithms that essentially in the dynamic algorithm also you will insert and delete the things. So there are some similarities then, but there are some differences essentially between them. Because especially in dynamic streaming, you have a limited space. In dynamic algorithm, generally you don't have this limited space. Good. So this is the problem. Streaming algorithms are generally hard. So if you have sublinear space, especially in N, so here we talk about more networks. There are others. So, for example, is a stream of numbers. You want to see what is the mean, what is the, these are heavy hitters or other things that you will say, what is the average or what are other norm of this number, that you can actually do it much faster. If there are N numbers, you may generally need only log N space. But whenever we talk about graph, the problem would be not that easy. With sublinear in N nodes, the life is difficult because we cannot remember that we have seen an edge before or even vertex before. And somehow there is some kind of information theory or communication complexity hardness. Even randomization does not help, essentially. This is like some of these problems like index or disjointness that I, again, talking about algorithmic lower bound course, which is available online on YouTube. You can actually take a look at them, but you cannot, it's not that easy. Even randomization does not help. But there are some relaxation that has happened. One is that essentially we are allowing linear in N space. So linear in N, what's the meaning of that? Is that, I mean, generally, if the graph has N nodes, then you can say that a space that you have is order N, or in general, O tilde N polylog. This is still sublinear if the number of, because the number of edges, M in particular, can be essentially omega N square. So this is sublinear, essentially, if the number of edges are like quadratic. But it is not sublinear in a. Other assumption that you can do it is the one that is called promised streaming. What is this is again some name that has happened. Actually, it's a good way to consider, and you can essentially say or express your research. In the promised streaming is that something is promised about the data. We can say, okay, this data is coming, but I have some information about it. Can you do something better than that? For example, one such kind of promising is that you know that the graph that is coming is a tree. The edges would be a tree. That is promised to you. Can you do anything? Here, of course, the goal is to, in this case, we want to get a strictly streaming. Means that we want to get sublinear in N, which is polynomial or logarithmic, essentially. That's a thing that we hope to get it, essentially. If we can get it, that would be great. If we have the promise, we want to get it. And good. As I mentioned, here there are, I mean, the promise is streaming. Something is promised, which is some kind of reasonable assumption about the input. For example, you know about something about edge density or graph structure. You know that this graph would be a sparse. It would be graph structure. It might be a tree. You may also get something about cost or size of the solution. So this is essentially the part that is talking about it, and I will talk about these things about the parameterized streaming. So parameterized streaming actually comes out of this promise streaming. So here in the parameterized streaming, the whole idea is that like you know that the cost of the solution is small. The whole graph might be n, the same thing that we talk about fixed parameter algorithm, but you know that the solution size would be small. Can you get something proportional to the size of the solution, not n? That we will talk more about it. But this is interesting. For example, for planar graphs, there was no non-trivial algorithm for any interesting problems on any graph almost. Maybe I want to get a max degree or something like this, or average degree or something like this, that you could do it in sublinear time. This is like the first paper that we had it. That was actually just interesting that they're referring to that as a first paper that we could get some non-trivial problem, like matching in planar graph, we could get actually sublinear space for it. we could get an approximation. And later, actually, it was first into the 2/3, and there are some other later work that they actually, some of them you can get even polylogarithmic. So that was the first non-trivial set of work that you could get some non-trivial problem like matching on the graph. Essentially, you can do it sublinear time. And this is in general getting, this is non-trivial because if you want to check whether the graph has this graph is a tree or not, that even is not an easy thing. Whether you know that there are n-1 edges in the graph, but you want to see whether it is a tree or not. Can you do in a streaming sublinear time? These are hardness that you cannot do it. So the other thing which is interesting also, this work that we were doing, these edges are coming in a random order. This is actually some work that we have done it with Hossein Esfandiari and Murtaza Moneemi. Later we had some other work with Alireza Farhadi. That actually that was a soda paper that we are actually improving on these results that we had it, early works that we had it here. And here, especially, I want to talk a little bit about parameterized streaming. And these are some nice things that, again, these are nowadays, I mean, if you go, for example, to the SODA or other conferences, the people actually work on that, and they have some papers. That there was a SODA paper just this year in 2024, actually, got accepted in parameterized streaming. This is somehow the idea of fixed parameter plus streaming. And so again, these different ideas of algorithm that I have mentioned, you can combine them actually and get interesting results. So good. So what is the parameterized streaming algorithm? So here you want to essentially, as I mentioned, here this is some kind of promised streaming in general, that you know the size of the solution would be small. You want to get a streaming with a space being a function of k. In particular, the solution size, which can be much smaller than n. More precisely, we want to get some kind of essentially a space which is f of k polylog n. And this, as I mentioned, the ideas come from fixed parameter algorithm. So there we try to get exponent, like essentially this was not bad. We try to get f of k poly n as a time for like fixed parameter algorithms. But here we want to get f of k polylog n for a streaming algorithm. And we want to say that report no if the size is greater than k. And again, here you can also consider, maybe I want to get, this is another one. So we have always parameterized, essentially, parameterized setting. We have, of course, here, for example, we have a streaming setting. And the last one also, you can consider approximation. Always you can consider approximation plus fixed parameter algorithm or approximation plus streaming. You want to say that, okay, if the size is k, I can give a solution of size 2k to you, but the space would be essentially, so this approximation algorithm is essentially used naturally for all of these problems, but I want to get the approximation, which is like 2k, but the space should be f of k essentially. So that's the interesting thing that we are talking. And one of the most famous problem that we talk about is our vertex cover. If you remember, vertex cover is actually a special case of set cover, in which all the sets have size 2 essentially. So vertex cover is a very fundamental problem. And interestingly, it's a very hard problem. We know that essentially on this, under the latest one is, I think we have a 4/3. You cannot get better than 4/3 approximation for vertex cover unless p is equal to mp. And you cannot get it better than 2. So no better than 2 if this is for essentially p not equal to mp, and this for vertex cover. And then you cannot get better than 2 unless this essentially under unique game conjecture. So it's a very fundamental problem, and it's very related to matching. Matching also is, as I mentioned, is like one of the, is a polynomially solvable, but it is still one of the hardest problem in P. Good. So here I want to talk about this concept of kernelization. So what is a kernelization? So you're given a graph G. What is a kernel? So here the idea is that you want to reduce the graph size. So from G, you want to find a kernel. It means that you want to reduce the input G to some graph instance which is G prime, and it is smaller than this. You want to have essentially this, you want to have this property that a solution on G prime corresponds to a solution on G. And you want to get the size of G prime is polynomial in K. Can be even exponential in K. And again, K is the size of the solution. For example, for vertex cover, the size of the solution is K. So from G, you want to get something essentially G prime, which is somehow is poly K, the size of it, or again exponential. Sometimes they will consider actually linear kernelization. If you can get, and this is as we discussed in essentially algorithmic lower bound course, this is essentially fixed parameter algorithm is equivalent to kernelization, that you can do if fixed parameter if there is a kernel for the problem. So one way is easy, the other way is a bit more involved. But the idea is that if you have a kernel of size K, or like poly K, f of K, then you can try all possibility on G prime. And you know that any solution here would be corresponding to a solution there. So you will just try all possibility here and you can get a fixed parameter algorithm. So kernelization essentially is very powerful. And as I mentioned, any problem that is SPT has a kernelization solution. But here the kernelization also, there's a research there is that whether it is a linear kernel, it is polynomial kernel, or sometimes even exponential kernel. For some problem, there is no polynomial kernel, again, under some complexity assumptions. So it's something that actually helps a lot if you know about these different essentially graph problems, and not only graph problems, also different type of algorithm. These kernelizations, we are using, this is in fixed parameter that people have considered it. There's a corresponding thing that essentially in streaming, we generally, this memory that you have, it's called a sketch. This sketch, it is some kind of, some kind of compressed form of the data that we have seen so far. This actually had some similarities, kernel and the sketch. And this is some of the things that we have used essentially to relate them and actually get, this is essentially starting the study of streaming, parameterized streaming. So consider the vertex problem. What is the vertex problem? You want to find a set of vertices S such that every vertex has at least one vertex in S. That's essentially vertex problem. So from each edge, you want to have at least one vertex select. So consider this algorithm for insertion-only model. So these edges are coming one by one. So you will maintain a matching M. So you're maintaining a matching M greedily on this graph seen so far. So what's the meaning of that? You will store an incoming edge in G prime. This is G prime essentially is the sketch that you will try to keep. So you will store an incoming edge in G prime if it does not share endpoints with the previous stored edges of that. Good. So any edge that is coming, if this edge does essentially is just does not share any endpoint with the vertices that you have seen so far, then and you can keep the set of vertices essentially that you have seen so far for this. You can have some sketch of them as well. So you will essentially, if it does not share an endpoint with the previous stored edges, so some edges you may essentially forget that you don't care. Those edges that you have, it's limited. If it does not share anything, you will add this one to your things. So, and for any vertex V in the matching, you will keep up to K edges incident on V in G prime. So any edge that is coming, if like the endpoints didn't appear, then you will keep it. Otherwise, if one of the endpoints is for each of these vertices, if it shares some endpoints, you will say that you just make sure that for each of these vertices, you keep only at most k vertices.
The first k?
The first k. And this is the insertion model. Yes.
The arrival order is still right.
This is no worst case here. Good. So what is the idea here? So these are two important. So that's the whole algorithm essentially. So this is the whole sketch essentially. How much space do I need essentially, as we discussed? The space that you will have it would be k squared, because two things that I want to say here. First is that, I mean, the matching size, this is the promise version. So we want to say that, and here say at this point, we know that the vertex cover has size k. This is promise given to us. There are some versions that you don't know. This is also interesting. You don't know what is the size of that, but still you want to get proportional to the solution size. So if the size is larger, you are allowed to use it, but you don't know in advance what is the size. But here, good. So here you have this k edges that are coming. As I mentioned, if edge appears, if this edge essentially, when this edge is coming, if the endpoints are not there, you will keep in the matching. And for each of these vertices, endpoints is there, you will keep at most k of them. Two things. Like this one thing is that you don't need to keep more than k edges from one vertex. Why? Because if these more than k edges are coming, you can just, you know that this vertex should be in the vertex cover. Why? Because these are like, if there are k plus 1 vertices here, if you know the size of the vertex cover is k, it means that if this vertex is not there, all of these k plus 1 vertices should be there. So it would be greater than k. So this vertex should be there. So you know that this vertex is in the vertex cover, and you can just keep it and just forget. And if you know if vertex is in the vertex cover, any other future edges that are coming, you can just ignore them because you know that you have selected one of them. The other thing is that you know that size of this matching should not be more than k. Why? Because each of these edges of the matching, you need to keep, you need to select at least one vertex. Good. So that means that the size of the matching should not be more than k as well. Now, and this is the idea. Now, at any time, if you want to get a solution for the original graph, if you want to get approximate solution or exact solution, you can actually, instead of running it on graph G, you can just running it on this graph G prime that you have. Because essentially all necessary information, you have kept it here, all important information. Good. So as I mentioned, so this essentially, as I mentioned, so this G prime mimics G. Anything that you can do it on G prime, you can do it G. Even approximation, if you want to get, you may get an approximation for vertex cover on G prime and just report it for G. That is fine. Also, the space. Why the total space that we have is at most k square here. Why? Because we have at most k edges on the matching. And on the 2k nodes of the matching, so we have k size of the matching, we have 2k as the size of this. And then for each vertex also, we will keep at most k edges. And note that this is the insertion model. So it is essentially order k square is the thing that you have it. And you can show that you cannot have any, for this problem, streaming algorithm, for vertex cover, you can say that there is no way that you can do a streaming better than like less than k square that you can show using communication complexity. So this is tight bound. You can get k to the 2 and you can get essentially solved. But there is an issue here. What is the issue here? The issue is that, okay, you obtain this, but this works for the case that insertion only. But what about the dynamic graph case? But again, so you can consider, like, for example, that happens a lot, like Instagram, LinkedIn, everything. The people friend and different, essentially. So there is insertion deletion. Or this algorithm now does not work. Why? The previous algorithm was very sensitive to the fact that these edges that are coming and you are seeing them, they are these edges are not deleted. Why? Because you can see that if, for example, one of these matching edges, you got some kind of maximal matching. If these edges are deleted, then then you need to add another thing to have it. That was based on the maximal matching in the graph. But if you one of these edges that you had it, as long as insertion, it was fine. But if it's deletion, this edge may be deleted. Then you may need to get another fine to maximal matching. But that edge may be gone, cannot see. So then this is actually interesting. So this problem we can solve for this dynamic graph problem if you are given this promise that at any time the size of the vertex cover is at most k. First, we are solving this one in this soda paper. We can simplify this one. And actually, you can also solve the problem if you don't know the k essentially in advance. But more interestingly, this is another paper that we had. This is actually lots of new papers on streaming are using this technique that we have done it here. This is, you can say, removing the promise. And this was an important problem. What's the meaning of that? The idea is that you have a graph, you will insert delete. You know that at the end of the day, the size of the vertex cover is at most k. Good. At the end of the day, in the middle, you may have a complete graph. The size of the vertex cover can be n actually, or n minus 1. In this case, can you still keep the data such that at the end of the day, I remove the thing such that the solution, this is size solution of size k. Can you report the solution of size k at that? This was actually, I was talking actually with Professor Sanjeev Khanna of UPenn. When I was mentioning it, like, no way you can do that. It's very non-trivial, actually, that you can do it. You see, you can mix, essentially. You can just insert, delete, and then change the whole graph. At the end, you know that it is at most k. And so if you keep these edges, lots of these edges that you keep it maybe all of them might be gone, essentially. And you have new edges that you have. This actually will show that you can do it. So here I want to talk about these two algorithms. So these things, to do that, I need two data structures in particular, k-sparse recovery and k-samplers. Good. So I think maybe like this is some more time I needed this one. So I will stop here and then we will continue next time and we will go through this one and we'll finish this and we will continue. After finishing this one, the big things, I talk about lots of these meta algorithms and meta approaches to handle this big graph. We will talk about some important network design problem and some of the solutions which are very elegant and can be used for other problems, like the approaches that have been designed. But I think I will end here.